Okay, let's talk about circular motion. So let's say we are having a circle here, and this is our circular track, and let's say we are having a motion in this circle, so this is what we call circular motion. So in linear motion, we have velocity here, which is denoted as v. As for circular motion, we also have velocity called angular velocity. Which is denoted as omega. The basic equation for the velocity is equal to displacement over time, since velocity is the rate of change in displacement. As for angular velocity, we have rate of change in angular displacement. So what is meant by angular displacement? So let me draw a line. So this line is directly attached to the center of the circle. So this one is another line. Okay. So let's say we are about to move from point A to point B. So this will be our distance here from A to B. So this one will be our angular displacement. Okay. Along the road from A to B, there will be a time taken, which is denoted as t. So basically we have angular displacement and we have time, so this will give us the angular velocity. Okay, let us move to the next part. Okay, so what is the true definition of angular velocity? Angular velocity, also known as omega. So angular velocity is actually defined as the rate of change in angular displacement. Okay, so the formula given here is angular displacement divided by time taken. Well, sometimes angular velocity is also equal to the angular displacement over the capital letter T. So this capital letter T is meant by the time taken to complete one cycle. Yeah, time taken to complete one cycle. So you have to remember that small t and capital letter T are totally different. So let us move to the next part. So let me draw another circle. Okay, as I mentioned just now, as we're moving in this circle, we have angular velocity, but at the same time we also have a motion which is called okay, here, tangential linear velocity, which is denoted as v. This v is a linear motion and is also and always tangent to our circular track here. So you have to remember that while we are moving in this circle, we have angular velocity and at the same time we also have the linear velocity. Okay, so what is the relationship relationship between the angular velocity, which is known as omega, and velocity, which is also known as v. Okay, so this can be presented in a formula here. So as we know that s is equal to r theta, so this s is the displacement when we move from one point to another point in this circular track. So this is A and this is B, so this one will be our displacement from A to B. So this one will be angular velocity as I mentioned just now. So this one will be our r, radius of the circle. Okay, so let me erase this one. Okay, as we know that s is equal to r theta, so what happened when I divide both sides by t? So s over t will naturally give us the v. So this one remain as r, while rate of change in angular displacement will give us the angular velocity. So this is one of the important formula need to be memorized. So v is actually equal to r omega. Okay, let's move to the next part here. Okay, so let's proceed to centripetal acceleration. Centripetal acceleration. Okay, first of all, we need to know that although, okay, let me draw a circle. Okay, this one will be my first line. Okay, let me use another color so that you can see clearly. Okay, oops. Okay, okay, as I mentioned just now, we have the linear velocity here, which is tangent to the circle. Okay, we have to know that first of all, although we move in this circular track with constant velocity, so that is still a centripetal acceleration occur in this circle. So why? Okay, at first we need to know that velocity is actually a vector quantity. Which is consists of magnitude and direction. So although we have a constant magnitude here, so our magnitude will be constant. So but the problem is here, the direction of the velocity is keep changing. And how can it change? Okay, let me give an example here. So I use green line, present. Okay, so this is yellow line. Oops. Okay, so this is my yellow line for oops. Okay, this is the fourth line. Okay, so this is considered as, wait, so this is considered as V1, this is my V2, this is my V3, and this is my V4. Okay, as you can see that while we are moving in this circular track, the direction of the velocity is always keep changing. So V1 is pointing to the right, and V2 is pointing upwards, and V3 is pointing to the left, and finally V4 is pointing downwards. So the direction is always changing. So this one will naturally give us the acceleration since since there is a change in direction. Okay, let's proceed in the next part. Okay, wait. Okay, this one as well. Okay, as we know that since velocity is a vector quantity, so I can present this v1, v2, v3 and v4 in terms of vector diagram. So let me draw a vector diagram here. So this one will be my v1. So let us follow the direction of the velocity. So this one is pointing to the right, and the v2 is actually pointing upwards. So this will be my v2. So let me join another, let me choose a different color. So let me draw another line by joining the v1 and v2 here. Okay, so this will be my v1, so this is my v2, and this one will be my change in velocity. So as we read from the vector diagram, we can know that v2 is actually equals to v1 plus delta v. So my delta v is given as v2 minus v1. So this is how we read the vector diagram. So what if I present this vector diagram in this circular track? Okay, let me draw for a while. So this is my v2. I drag this v2 into v1 here, move to v1 here, so that they can attach to each other. Okay, okay, this one will be my change in velocity. Okay, so okay, let me draw another vector diagram for v2. I drag this v3 to v2 here, so that I can represent the vector diagram. Okay, and of course the direction of v3 when I drag to v2 here, so the direction of v3 must be the same as this one. Okay, so this will be my change in velocity. Okay, so this, okay, let me draw a final line. So this is my v4. Okay, so this will be my change in velocity. Okay, okay, so let me label it so that you can see it clearly. So this will be my delta v. So this one is my v2 here, so this one will be my v3, and at the same time will be delta V. So this one will be my V4. So, and as well, this one will be my delta V. Okay, as you can see that the purple line represented in this vector diagram for every point of this circle is actually pointing towards the center of the circle. Okay, so this means that the change in velocity, which is also known as delta V, is always pointing towards the circle. Pointing, oops, I write it wrongly. So, okay, pointing towards the circle, center of circle. Okay, what does this means? So what does this statement means? So let me briefly explain. Okay, as the direction of the velocity keep changing, we know that the direction of velocity keep changing. As the velocity changes from v1 to v2, which is from here to here. So the change in velocity, we know that is always there will be a change in velocity. So this is delta v, and at the same time, from v1 to v2, there will be a time taken, which is denoted as t. So basically, we have delta v, which is change in velocity, divided by the time taken, will naturally give us the acceleration. So this means that the direction of the acceleration is also pointing towards the center of the circle. Pointing towards the center. I hope you can see clearly since there is not enough space here. Okay, so this is how we determine the direction of velocity. So let's proceed to the next part. Okay, so let me erase this one. Okay. All right. So let us move to the next part. Let me see what is the next part. Okay. So okay, let's look forwards about the formula for centripetal acceleration. Formula of A. So okay, let me think for a while. So the basic formula for the centripetal acceleration is actually given as v omega. Okay, just now we mentioned about the relationship between the linear velocity and the angular velocity, which is given by the formula as v equal to r omega. Okay, basically we can directly substitute this v into here, this v. So v is equal to r omega, so this one is another omega. So finally we get a is actually equal to r omega square here. So what if I subs omega into acceleration formula? So basically we will get A is actually V, so this one is V over R, so finally we will get V squared over R. So this is another two formula which is need to be memorized. Okay, so let's proceed to the next part. So the definition of the acceleration is actually defined as the rate of change in let me think how to represent this sentence. Okay, rate of change in velocity. Okay, if you want to extend the sentence is also acceptable, which is directed towards the center of the circle. Directed towards the center of the circle. The center of the circle. Alright, this is the definition of acceleration. So let me, okay, I just write a symbol here, but actually is acceleration. Okay, so let's proceed to the next part. The formula is given by acceleration is actually equal to the rate of change in velocity divided by the time taken. Okay, let's proceed. Okay, let me see for a while what's next. Okay, so we have done two parts, so let's proceed to centripetal acceleration. Centripetal acceleration. Alright. Centripetal acceleration. Okay, let me draw another circle. Okay, so this one is a line which is joining to the center. Okay, as we know that we mentioned just now, the acceleration is actually pointing towards the center of the circle. So basically, I wrongly write again. This one should be centripetal force. So my mistake, sorry. Centripetal force. Okay, as we know that the centripetal acceleration is pointing towards the center of the circle, as I mentioned just now. So the resultant force while we moving in this circle, okay, as we having the motion in this circular track, so our resultant force, which is also known as centripetal force, is also pointing towards the center of the circle. So the direction of A, acceleration, and the force is actually pointing toward the center of the circle. Okay, so what is the formula for the centripetal force? Okay, basically force is actually equals to ma. So just now we talked about the formula for acceleration, which is r omega square, and a is actually given as v squared over r. So this both a can be substituted in this formula. So what we get is f is equal to mr omega square as well as mv square over r. So this is the formula for centripetal force. Okay, one thing need to be reminded that is okay, let me draw another circle here. So this is my circle. Okay, so this one will be a line and two lines. So this will be point A and this one will be point B. As we know that from A to B there will be a distance here, which is our arc length. So this is our distance, or aka arc length. Okay, arc length. So from A to B, this will be our distance. So as we know that the centripetal force is always pointing towards the center of the circle. So as you can see that the centripetal force and the distance from A to B, or I can write here also as centripetal force. So the direction of the force and the direction of the distance, which is from A to B, as you can see that is always perpendicular. So I can conclude that S is actually perpendicular to F. So we know that work done is the product of force and the dot product of displacement. So since force and displacement is always perpendicular, which is 90°, so our work done is naturally given as 0. So there is no work done when we were having the circular motion. Okay, so let's proceed to the next part. Okay, let's proceed to the horizontal circular motion. Okay, so let's say this one is a string. So this one will be our string here. Okay, consider we are standing in the center of the circle. So at the end of the string there will be an object which is denoted as mass m. So we strictly write as weight is actually equal to mg. So this will be object which is tied at the end of the string. So consider we are standing at the center of the circle. So we are allowing this object to undergo the circular motion. Okay, we know that when we are allowing the object having the circular motion here, so there will be a tension between us and the object. The string will produce the tension. Let me write more clearly. So the string will naturally produce tension between the object and us, which is standing at the center of the circle. So this tension is naturally given as the centripetal force, which is mv squared over r, or mr omega square. Okay, so that's all. This one tension is also can be denoted as the resultant force. Let me write it clearly. Resultant force. Okay. Or centripetal force. We all know that. Centripetal force. Alright, that's it for the horizontal circle. Okay. Okay, let's move towards the vertical circle. Motion in vertical circle. Okay, motion in vertical circle. So just now we talked about the horizontal circle. Oops, I write wrongly. So just now we talked about the horizontal circle, so let's proceed to the vertical circle. Motion in vertical circle. Okay, so let's say we're having another circle here. So this will be our string again. This will be our string. Okay. At the end of the string, we are tied to an object which have a mass denoted as m. So we have a weight mg. Okay. Let's say, let me draw another circle here, another line here. Okay, so this is my mg. So these two objects is basically the same. So this will produce tension. Okay, so this is the center of the circle. So the string will actually produce tension here. So as the basic, we know that. Okay, this one will be our mg cos theta. Okay, let me drag to the right. Okay, this one will be our mg cos theta. So this one will be our mg sin theta. Mg sin theta. So after resolving this from this weight, which consists of vertical force and horizontal force, so this one will be our vertical force, which is the same, how do I say that, which is the same phase as the tension which produced from the string, but with opposite direction. Okay, so basically our resultant force, or known as centripetal force, okay, let me write another resultant force. Okay, mv squared over r is basically equal to the tension minus the weight of the object, which is the vertical component after resolving from the resultant force for the weight. Okay, so this is our basic formula for the vertical circle. Okay, let me erase this circle here. Okay, this is quite hard to adjust. Okay, let me draw a new circle here. Okay, so let me draw a line. Okay. Okay, let me erase all. Okay, so let me denote this as point A, point B, point C, and finally point D. Okay, as we mentioned just now, the resultant force or centripetal force is actually given as tension minus the mg cos theta. So tension minus the weight of the object will naturally give us the centripetal force. Okay, so consider this one is a vertical circle. So we are allowing the object to having the circular motion in this vertical circle. Okay, let's say we start from point A here. Point A, okay. So since we start from point A, so our degree will basically equal to 0 degree, since we start from point A. Okay, 0 degree cos 0 degree will naturally give us the T minus mg, since cos 0 degree is 1. So this will be our point A. So what about point B? Okay, when the object approach point B, so at point B, our theta is basically given as 90 degree. Okay, since we reached here at 90 degree, so cos 90 degree will basically give us 0. Okay, so our centripetal force is actually equal to the tension of the string. So I denoted this one as TB. So this means that the tension occur at point B is actually equal to the centripetal force. So this one will be our point A, TA. Okay, what about TC? Okay, at TC here, so this one is 0 degree, 90 degree, and this one basically will equal to 180 degree. So cos 180 degree basically will give us -1. So what we get is T plus mg. So why this happens? This is because when the object reach point C, the tension of the string as well as the weight of the object is pointing towards the same direction, which is towards the center of the circle. So this basically will give us T plus mg. Okay, TC. Okay, what about TD, which is 270? 270 will naturally give us 0, since cos 270 degree is actually 0. So mv square over r is actually equal to the tension of the D, so which is basically equal to TB as well. So this is how we determine the motion in vertical circle. So this enables us to find the tension of the string when we are having the motion in vertical circle. Okay, so let me erase. So let me erase this one as well. Okay, this one will be our point D. So what do you think? Which point along this among these 4 points? Which point will be our minimum tension? Minimum tension. Okay, which point will be our minimum tension here? So basically minimum tension is actually at point C. This is because, as we mentioned just now, mv squared over r is actually equal to the tension at point C plus mg plus the weight of the object. So Tc is actually equal to mv squared over r minus the mg is basically equal to 0. Oh, not so. I'm sorry. Let me erase this one. Not totally 0. Should be approximately equal to 0. Wait. I think not approximately. Should be totally 0. Since at point C, there is no more force acting upwards. There is no more force acting upward at point C. So our weight and our tension is always pointing downwards. So Tc is actually equal to 0, since mv squared over r minus mg is equal to 0 here. Okay, let's move to the next part. Okay, let me see for a while. Okay, let me see. Okay. Okay, let us proceed to the final part, which is the conical pendulum. So this will be our final part for this chapter. Alright, consider we are having a pendulum. The pendulum is actually attached to the ceiling. Oops, let me erase this one. Okay. So this one will be our ceiling here. So this one will be our string. Okay, string. Sorry. So this one will be our string. So let me draw a dotted line here. Okay. So this one will be our pendulum here, the bob. Okay, let's say we are allowing the bob undergo the circular motion. Okay, as we know that this one will be our weight of the bob, so this one will be our tension here. So how can we resolve how can we resolve this between tension and the weight of the bob so that we are able to find the we are allowed to find the resolving formula. Okay, while we are resolving this pendulum, so we must know that the tension between the tension and the weight of the bob, the tension will basically give us the, okay, so let me erase this T here. So the tension will basically give us the okay, T sine theta, and this one will be our, not T sine theta, should be T cos theta, since the angle we calculated starts from here. Okay, so this one will be our T cos T sine theta, so this one will be our T. Okay, what is the relation between from the diagram, what relation can be concluded? So basically T cos theta, as you can see that the vertical force and the weight of the bob are actually in the same phase, okay, but in different direction. So we can conclude that T cos theta is actually equal to the weight of the bob. Okay, so this T sine theta is actually equal to our centripetal force. Okay, so we have two equations here. Sorry, we have two equations here. So sine theta over cos theta will give us the tangent theta. So this one will be our mv square over r, so over mg. So cancel this one. So eventually will give us the v square over rg. So this is how we find the angle of pendulum, which is undergoing the circular motion. So from this formula we are able to find the angle, or we can find the linear velocity. So this one will be our linear velocity for the bob using this formula after the derivation. Okay, so that's it for the chapter of circular motion. I hope you understand further after watching this video. So thanks for watching. Okay.